Hello. Since my title slide has the word network in it so many times, I need to start by answering the question, what is a network? So a network is a set of nodes connected by edges. We often draw it this way. So this is a drawing of a network with 5 nodes, 1, 2, 3, 4, 5, and 6 edges. For instance, there's an edge between 1 and 2 here. We often represent these nodes as a set 1, 2, 3, 5, and edges represented by set of edges. So 1, 2 is the set 1, 2. This is a very simple version of the graph, and it doesn't give you much sense of what we're going to be doing with it, but we'll have the whole talk to talk about that. Before we leave this, I'll also mention that these nodes themselves don't have to be numbers. They often can be more complicated objects. These edges may be directed, often with arrows will indicate the directedness. So there could be an edge not between 1 and 5, but from 1 to node 5. These could be weighted. They could have capacities. These can be much more complicated, and we'll see many more complicated versions in a moment. All right, so for the first part of the talk, I'll start by giving you some examples, more complicated examples than I started. And we'll also talk about some graph analysis or network analysis problems. Then before telling you what NetworkX is, I'll also need to tell you a little bit about sort of the data structures and algorithms that we use to work with networks. For the second part, I will focus mainly on telling you what NetworkX is, going over its functionality and features. I'll briefly tell you a bit of our past and what we're currently working on and the future. And then I'll conclude by showing you where you can learn more and also asking you to help get involved with NetworkX's development. So for examples and problems, there are many, many examples of physical phenomena that benefit from network analysis. So for example, there's networks of highways, railroads, power grids, supply chains, financial networks, telephone networks, computer networks. And here we've got a picture for an example of a physical network overlaid on top of a map of parts of North America. These are cities and locations where they occur on the map. And what we've done is we had 128 cities in our data set and distances between all pairs of cities. Just so there's not too many edges, we only drew edges very close together cities. So you had to be closer than 300 miles to have an edge. So there's no long edges. And then we colored the nodes by their degree. So purples have very few connections. Or very few cities are within 300 miles, where this yellow one has many, many cities within 300 miles. The size of the nodes are based on the population. So this is a smaller city, but it's very close to many cities. And this is a large city, but it's not very close to any other cities. And for these kind of maps, you often think of things like what is the shortest distance or shortest path between 2 cities or 2 nodes. And so in addition to that, you often have on these maps, if you're thinking about these physical systems, you're constrained with the capacity of these edges. So you're interested in maximizing flow across them based on the capacities. Biological phenomena, there's again many, many examples. So disease spread. Right now, you hear contact tracing a lot in the news, and that's essentially trying to find these travel these networks where individuals that are in close proximity to each other consider having a link. And that link could be a possible transmission vector. Gene expression. So this is an image over here from a public data set. This image, as well as the previous one, are on our gallery, and I'll talk about the gallery a bit later in the talk. But if you go to the gallery, you can find these images, and you can find the code and the data as well. And you can play with it and figure out exactly what's going on. But here what we do is each of the nodes is a gene, and the edges are associations between genes, functional associations, so genes that are active in the same sort of metabolic process or whatever. And we've colored the nodes, and the color is based on community structure. The size of the nodes here is based on something called betweenness centrality. So we've already mentioned shortest path between 2 nodes. So each of the nodes in this graph, each gene has a shortest path between 2 pairs of them. And if you map out all of the shortest paths, then look at each individual node and see how often it falls on an average, how many of these shortest paths it falls on, you'll get a sense of its betweenness centrality. All right, so in addition to gene expressions, there's metabolic pathways, ant colonies, food webs, brain regions, river basins, plant pollinator, predator prey, and on and on. Social phenomena. So here we've got individuals or entities within inside of government or business or social clubs or churches, social media, schools, military, and they may have, maybe they work together or they or direct reports or, maybe they're on the same team or they sit close to each other or some other way they're related, they're friends, social media, Facebook friends, Twitter followers, on and on. So I'm sure everyone at this point has a very clear idea of what kind of networks we're talking about, and you probably have some sense of networks that you're interested in yourself. So just a summary here from networks from data. The nodes can be many, many things. Basically some sort of agent or entity, person, animal, ancestor, city, gene, brain regions, random variables, on and on. And edges, there's lots of ways you can have edges. So there's some sort of interaction or friendship or proximity or some kind of co-occurrence. You show up at the same place or you both, things are physically proximate. There could be expert knowledge where you just happen to know the network structure of something. Correlation and conventional independence. And I'll say a little bit more about the correlation one. So for things like brain regions, you might be interested in, watching some person in the fMRI or some sort of neuroimaging scanner. And that scanner can tell you each region's activation level over time. And you're interested in how these regions communicate together or coordinate. And so a very simple way of looking at the graph or network structure there is to just look at these time series data for each of these regions. And then compute a correlation matrix. So, for example, these 30 some regions of the brain, say, and then there's a correlation score for their time series data in each of these entries. So, this is brain region 5, say, and brain region 4, and then that's the value in color. So red would be 1 and dark blue would be -1. And this corresponds to a graph where it's fully connected. And then there's weights on every edge that correspond to these correlations. We can take that correlation matrix and we threshold it. That's what I did with this. I looked at a histogram of these correlations, and then there was an obvious cutoff. I chose that at 0.6. And then everything above the 0.6 or below -6 becomes a 1. Everything in between those ranges becomes a 0. And then this is the inferred graph. So essentially, I've just drawn the graph here based on, for instance, 2 and 3 are connected. So that's probably there, right there. It's 2 and 3. Okay. So just really to summarize again, so some network analysis problems, we've mentioned a few. So shortest path between two nodes, community structure we saw in the genomic data. You also might be interested in identifying structures similar across networks, or analyzing link structure, which we used in determining the community structure as well. All right, so say a little bit about more of the programming aspect of this, data structures and algorithms. So first, just what kind of data structures are we going to work with? We've mentioned this graph to begin with, and we could just put in these sets, but they're not going to be very convenient. So one of the convenient ways to deal with it is adjacency matrix, which was very much what we saw in that threshold graph. And so here what we've got is there's an edge between 1 and 2. So 2 and 1, 1 and 2 both have a 1. There's no edge between 3 and 5. So if we go 3 and go down to 5, we see a 0. Or if we go from 5 and go to 3, we see a 0. And I should just say, so you'll often see in this in real graphs as they get bigger and bigger. So as n increases, you'll see more and more zeros in here. So this can be a very inefficient representation of a graph with all these zeros. Of course, there's sparse matrices support to handle those things as well. But adjacency lists are another way, and they're often used for a couple of reasons. One is they immediately don't have the zeros. So if you have sparse graphs, they're very efficient. The other thing is that many algorithms in graph and theory and network science have the flavor of from a node, look at all of its neighbors. So that's exactly what the adjacency list captures. So what we have is we represent the graph by looking at the adjacency structure for all the nodes, so 1 through 5 in this case. And this is all the neighbors of 1. So and in this sequence, we've got, if you want to explore the neighbors, you would first look at neighbor 2, then neighbor 3, and then neighbor 5, and so on. And we'll basically use this adjacency list as the underlying representation of graphs in NetworkX, although we won't use this linked list structure. We'll talk a bit more in a second about it. Okay, so let's just look at a couple of the algorithms or problems in more detail. So shortest path problem we've mentioned, and there's many algorithms to solve this. I've just listed a few here, but Dijkstra's algorithm, they have different flavors. So Dijkstra's algorithm is faster than Bellman-Ford algorithm. However, Bellman-Ford algorithm handles negative weights, where a Dijkstra algorithm doesn't, say. Some of these are heuristics to speed up some of these other algorithms. And then these last two are not just give me a node and I'll tell you the shortest paths from that node. These give you all pairs shortest path. And Johnson may be faster on sparse matrices than Floyd-Warshall, for instance. Applications, driving directions using online maps is an obvious one, but also in plant facility layout, obviously, and then subproblems for many problems. Like we saw in the between centrality, that was a notion that you want to know about how many of the shortest paths in the graph are you on. And so to do that, you can need to compute all these shortest path problems, or all pair shortest path first. Another type of algorithm, PageRank, and this was made famous by Google, where the motivation for them was, you do a web search and they find a bunch of web pages that are useful for your search query, but they need to figure out which one is the most important one, or which one would you most want to see, or somehow to rank those so that they present them to you where the most useful ones are at the top. And the idea was to basically use the link structure of the web. So the web itself is a graph where every web page is a hyperlinked document that points to other web pages. And the idea of the PageRank algorithm is you want to assign all the web pages some sort of numerical rank based on how important they are, using the fact that you believe that important pages are linked to by many other important pages. This has applications in many areas. And search was really the sort of where it was most celebrated. But in this PageRank Beyond the Web review article, 2015, I just took some of the list of things. So here, there's a bunch of versions of this PageRank algorithm that are applied to protein and genomic, so biological data. Here it's in citations, academic citations. Over here, we've got some examples in computer networks. But there's many more. And if you're interested, you can just read this article. All right, so for the second part of the talk, what is NetworkX? So NetworkX is a reference library for network science algorithms in Python. Its key features include it's easy to use and install, has a flexible data structure, broad range of algorithms, supports many file formats. It's has good documentation, simple design, well-tested and open source. We have a core developer team of 9 individuals that support and review and maintain the software, with contributions from over 430 people. It's constantly growing. Even now we have many PRs, pull requests on GitHub from first-time contributors. I'm hoping some of you in this audience listening to me now will soon become first-time contributors, and even be greater if some of you guys would stay along and become core developers eventually. Okay, so NetworkX is one of the technique-specific libraries in the scientific Python ecosystem, along with scikit-learn, scikit-image, stats models, and pandas. Just in the layer above SciPy, Matplotlib, and NumPy. It's used by many of the application and domain-specific libraries above it, AstroPy, BioPython, and so on. Scikit-image also imports NetworkX and uses it for recency adjacency graph for image processing. Before I go further, I just want to give you a simple example. So we import NetworkX as NX always, just like you import NumPy as NP. So here's this graph, and we're going to just manually create it. So first you create an empty graph, and then we're going to add edges. So we add edge AB with weight 4. Then we add edge BD with weight 2, and so on. And at this point, we can ask what the shortest path is in this graph from node A to D. And we're going to ask it not just the shortest path, but the shortest weighted path by telling it this keyword is weight. And so if it was just the shortest path, either these ABD or ACD would work. But since we're interested in the shortest weighted path, 4, 2 is going to be shorter than 3 plus 4. So it returns A, B, and D. Our basic data structure for a graph is a dictionary of dictionaries. So the very first outer dictionary is keyed by the nodes of the graph. So since these are keys to a dictionary in Python, it's any hashable Python object. So if you want to know what the G nodes are or what your nodes are in type G nodes, you'll get whatever you put in, anything hashable. And the edges are going to be tuples with optional edge data. And this is going to be a dictionary with its neighbors as keys. So it has a very natural syntax. If there's a node U in the graph, then G of U returns a dictionary of U's neighbors. And if V is a neighbor of U, then GUV is going to return the edge attribute dictionary of the edge UV. We can also ask, is N in G to test whether the graph G contains the node N. And we can also loop over all of the nodes in G just by saying for N and G. The other thing nice about this is it's very efficient. It's a adjacency list representation, which we already discussed is nice for sparse graphs that occur often in natural data. We also, finding edges and removing edges is just 2 dictionary lookups, and Python dictionaries are highly optimized. So this representation is very efficient. All right, to give a little more concrete look at what this looks like, that graph G, I've just asked NetworkX to just print it out as a dict of dicts. And so you can see the outer dictionary is keyed by the nodes A, B, C, and D. And node A has a dictionary associated with it with B and C, which are its 2 neighbors. And the value of the AB is the weight 4. Right, so this can get more and more complicated. We happen to have weight and A's and B's, but these can be any hashable objects. And then this can contain any sort of thing you want, basically. Okay, we provide 3 main graph types, data structures for 3 main graph types. So simple graphs, directed graphs, and then as well as graphs with parallel edges and self-loops. This last one, so this is graphs, these are digraphs, and this is multigraphs in our language in NetworkX. And for all these graph data structures, it's the same sort of dict of dicts. So nodes are any hashable Python object. In particular, it could be, in addition to being integers or strings, it could be just arbitrary text. It could be images. It could be XML. And then the edges can have arbitrary data. So, classically, you'll see things like weight and time series, things like that, capacity. These graph objects also have some methods to view, query, and modify the graph. So we can view the nodes and the degree and the edges. We can also find out the number of nodes, the number of edges. We can query if the graph is directed. And we've already seen we can add edges to the graph with add edges. We can also modify the graph by adding a bunch of edges at once from some container. We can also remove edges and remove edges from containers as well. And so in addition to creating graphs manually by adding edges, we also provide several graph generators. So there's classic graph like barbell, the complete graph, star graph, many, many more we provide generators for. So you typically need to tell these functions how many nodes you want this graph on, maybe some other parameters you can look up. We also provide generators for many, many random graphs, the classic Erdős-Renyi, as well as graphs that are more useful in social network analysis. In addition to these random graphs, we've got expanders and lattices and degree sequences and special social networks and many, 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 many more. In addition to the data structures and methods and generators, we have operators. So we can take a graph and can create new graphs from that graph. And so one way is to take a graph and get some subversion of it. So, maybe there's a graph and you only look at the subgraph on a certain set of nodes. We can compose or combine graphs with Cartesian product, union, disjoint union, compose. We can also get the complement of graphs. So if the complement of a graph would be wherever that graph has an edge, the complement does not have an edge, and wherever it does not have an edge, the complement does. In addition to manually building the graphs up or using these other generators, if we have some data, there's many different file formats we can read those graphs in. So it's easy to put things in an adjacency list or an edge list. We also support, instead of these plain text files, some of these other formats, which are formats used by other graph algorithms. So we can use these file formats to transfer data back and forth. Dot is a classic, so we'll talk about GraphViz again in a second. And there's GML and GraphML. Basically, these would be things you need to know about if you get one of these file formats. And then you can just look it up. So I won't go into too much detail about it. We also provide drawing and visualization routines. So the primary way we provide graph drawing and network drawing is through Matplotlib. So this graph I showed you earlier, this is how you go about drawing it. So first I used a circular layout just because I wanted it to look nice. And then I wanted to draw these edges weighted. So I first needed to figure out what the widths of these edges would be. And I used weights. So G edges returns the tuple of edges. And I'm asking it to also include in that tuple the weight as well. So you get a 3 tuple for each edge. So you get the 2 vertices as well as the weight. And then we're just going to make a list of those weights for each of those edges. And then we can draw NetworkX by giving it the graph and telling it the position and the weights. And then I also wanted to put these little numbers in. So we need to get the labels. And then we can use the draw NetworkX edge labels to label the edges. And if you go to the gallery, you can see many, many more examples. Here's just a few of them. So you can include since it's Matplotlib, you can include all kinds of other Matplotlib graphs and figures. And if you're interested in seeing how any of these are made, just go to the gallery and you can get the code and play with it yourself. We also support drawing graphs through GraphViz. GraphViz is probably the biggest classic example of a graph drawing library. And it uses this thing called the dot language. So first we create a GraphViz graph. And if we do a draw, we basically call GraphViz on the dot under the hood to create the PNG. However, it's sometimes useful to get the dot file itself and manually edit it. And in that case, you can just write out the dot file. And then this is what that graph G looks like from GraphViz. All right, so we provide many, many algorithms. I'm not going to go through all of these details. This is just a subset, but I was trying to give you some sense and thinking that maybe some people in the audience would recognize some of these measures depending on what kind of problems they're interested in. So we looked at centrality, for example. We looked at between-us centrality, but we provide many other centrality measures that are useful in social network analysis when you're trying to figure out what the important nodes in a graph are or a network are. Clustering, community detection, link analysis like PageRank, shortest path, et cetera. Flows for those physical networks, transportation networks we were talking about, flow networks. We also support linear algebra. So, most of these algorithms use that dictionary of dict graph representation. However, the linear algebra stuff, we need to represent them as matrices. So we provide data structure support for turning your graph into an adjacency matrix or an incident matrix or a Laplacian matrix, which are very related graph matrix representations of graphs. And then once you get in this matrix form, these are all symmetric, so you can compute eigenvalues and or they're squares, so you can support eigenvalues. Instead of looking at this, I'll just give you this example from the graph. So here, this is another gallery example It's just the histogram of the spectrum of a random GNM graph. So you create this GNM graph, convert it to a Laplacian matrix, and then look at its eigenvalue decomposition, and then take the eigenvalues. And the eigenvalues will be between 0 and 2 for Laplacian matrix. And the smallest one will always be 0, but the second smallest one, which is also called the algebraic connectivity, may or may not be 0. If it is 0, then your graph is disconnected. If it's not 0, your graph is connected. And the vector, the eigenvector associated with the second smallest eigenvector is called the Fiedler vector, and that can be used for partitioning the graph as well as for embedding the graph in Rn, spectral embedding. And if you embed your graph in Rn, then you could do something like k-means to cluster it. So it's often used for some sort of clustering, either through partitioning it directly or through embedding, followed by another clustering mechanism. All right, so conversion. NetworkX, given its position, we basically provide to and from functions for things at our level or below. So you can take a graph and convert it to or from a dictionary or a list or a NumPy array or a SciPy sparse matrix or a pandas data frame. Other graph libraries, recently iGraph, which is not a Python package, but provides Python bindings for graph and network analysis. iGraph recently added to and from functionality to support NetworkX graphs, which is great. There's also many of the application and domains, mainly application-specific libraries that support NetworkX to and from functionality if they have specialized networks. So there's some of the deep learning graph libraries, as well as I just gave some examples here from geospatial data analysis. There's probably more that I'm not aware of. So in summary, complex network analysis with NetworkX, it's flexible, it's easy to use, and it's powerful. It's flexible because the data structure, this dict allows arbitrary edge data and node types. It's also easy to read and convert to many data formats, both file IO as well as the dictionary and other formats. And it's interoperable with other graph and array libraries. It's easy to use, so it's a pure Python library, so it's inherently multi-platform, and it's very readable code. It's well documented and well tested. It's powerful, so there's hundreds of functions for creating, manipulating, measuring, studying, and visualizing networks, and it handles data sets with 100 million nodes or 10 million nodes and 100 million edges. That's really the limit of our capacity, and that requires that you have some care in your analysis as well as sufficiently beefy hardware. But much smaller networks are very easily handleable by NetworkX. If you get much bigger than 10 million nodes, 100 million edges, you'll probably want to get a different graph analysis library, or come join us and help us develop faster algorithms and better support. Okay, so past, present, and future. I just want to quickly give you a timeline, give you a sense of how long these ideas and libraries been around. So in 1998, the creator of Python, Guido, first proposed using a dictionary of list to represent graphs. A few years later, David Epstein proposed a dictionary of dictionaries, which is what we ended up doing. Eric and Peter started NX at Los Alamos in 2002. They were interested, at the time, they were doing some analysis of a disease spread. So NetworkX really just started life as a research project. In 2004, it was publicly announced at the SciPy conference, annual conference. And the following year, it was released as open source software after going through whatever the Los Alamos process was. Over the next 5 years, it attracted many, many more developers, continued to be driven largely by research, but grad students and other young scientists and faculty were contributing stuff as well, based on their own research. And in 2010, NetworkX 1.0 came out, and it continued to develop, continued to be used. And as it got more and more advanced, and Python 3 became more and more useful, and there was some desire to sort of do a major interface redesign to make it much more Pythonic 3, essentially. And that was a very ambitious project, and maybe it was a little bit more than, we bit off more than we can chew at the time, so it was very hard to land 2.0. And at the same time, while we were trying to do that, many of our core developer team graduated their PhD programs and went into industry or joined other projects. And so our developer team, shrunk quite a bit after 2.0. However, we did continue releasing regularly with more algorithms, improved algorithms, all kinds of bug fixes. Basically every 6 months we had a release. And during this period, we've done a lot of cleanup, and we're right now in the midst of trying to do a lot more of this in the hopes that we can grow in the future to regrow our developer team. So recently we've added and improved algorithms. We've improved our testing infrastructure. We switched from Nose, which is no longer supported, to PyTest. We also removed a ton of old legacy code, both from supporting the pre-NetworkX 1.0 libraries, but also from our supporting Python 2 and Python 3 at the same time. We also recently adopted Black for style. So that has really helped us in terms of reviewing PRs, because it's very unpleasant for both the reviewers and reviewees if when someone tries to contribute a lot of code and you're just talking about what the code style should look like. So now we've got this program that just runs, and that's taken that decision and discussion out of our hands, which is nice. Allows us to focus more on the algorithms and contributions and speed. We've also done a lot of work on the sort of structure and process. So we have been around since 2002, but we had never had a logo until now. We just recently joined NumFOCUS. We've also finally formalized governance and decision-making processes, and we acquired NetworkX.org just recently. And we've also, in preparation for trying to grow the developer community, we've spent some time trying to develop and formalize our community structure. So we've adopted a code of conduct. We've added a mission statement and values, and we've improved our contributor and core developer guides, created a roadmap and enhancement process, proposal process. And we recently got our first NetworkX grant through the Chan Zuckerberg Institute's Essential Open Source Software for Science program. And as a part of that, we'll be making a major release. So we have a planned release schedule of releasing 2.6 at the end of 2020. Early 2021, we'll release NX 3.0. And the goal is that at the NX 3.0, we have cleaned up a bunch of our messes, and we're really in a position for growth. And so we're going to be very aggressive after NetworkX 3.0 and trying to grow and recruit new developers, grow our community and recruit developers. And this is part of why we're talking now, to get people excited and hopefully have some new contributions. So learning more and getting involved. This is just a screenshot of our website. So if you go to networkx.org, you'll be able to get a link to our mailing list, our issue tracker, our source. You'll also find the release notes and be able to download and look at the documentation for the most recent stable release. And if you go to the latest and hit on doc, it'll take you to this page. I encourage everyone to look at the tutorial if you're new to NetworkX. Also the gallery, here's some of them. You've seen some in the talk already. Basically you can go here, click one of these, and that'll take you to another page where you can get the code. And then you can take the code and run it yourself, generate the figures. It's a great way to learn. Also, there's a reference library with an API guide for things. I also do a lot of searching here for functions. And then if you're interested in joining us, go to the developer guide. And the first thing you'll see is this code of conduct. So I think that's, the very first place to start is read the code of conduct. If you're new to the project, then go to the contributor guide, and then maybe the mission and values. And then the rest of it, you don't need to worry about right away, although you're welcome to look. But the contributor guide and the code of conduct should basically be enough to get you ready to go and start working and contributing. And then how to help. So again, go to GitHub, our NetworkX repository on GitHub. And we're looking at, lots of things, but, algorithms and documentation. So, the traveling salesman problem was recently in the news. And we don't have the classic Christofides algorithm. We also have some social network analysis community detection, but we could use a lot more. Many of us in the developer community are interested in biological networks and would love to see better support. There's also been a lot of work recently on graph. There's been a lot of discussion of work on graph isomorphism. So I think that this will probably, we'll probably have some new graph isomorphism algorithms implemented in the next few months. Documentation. So if you don't really want to contribute to the code, but you're interested in doing some more long-form documentation with code, we would love to have improved gallery examples. So, if you have your own, data set with your own analysis and examples, you might be able to find a little, nice graphic and share it with others. We'd love to have that. We also are recently adding more of a notebook binder style tutorial on how-to documents, which we'd love to see things. For example, domain-specific introductions, NetworkX for geospatial scientists, or NetworkX for neuroscientists or neuroimaging people, as well as education materials. So thank you very much for listening. And we are going to have a sprint at this PyData Global. I hope you join us there. And I hope to see you guys on GitHub as well. Thanks a lot.